Okay, so what is chemical bonding? Right, so bonding is what essentially forms our molecules. Right now, we kind of have some sort of idea with respect to bonding. What two types of bonds do we have right now before we even start talking about this? We have ionic bonds and we have covalent bonds, right? And so what is the difference between them and just kind of our understanding of it right now? Ionic bonds, what happens? There's a transfer of electrons, right? We form ions, and it's the attraction of those two ions that actually form the bond. What about covalent bonding? What's happening in covalent bonding? They're sharing, okay? So that's where we're kind of coming in with the understanding that we have right now, okay? So in the next two chapters, we are going to introduce you guys to three separate bonding theories. The first one is called Lewis theory, and it's essentially what this chapter deals with. The second is valence bond theory. And the third is molecular orbital theory. So why do you think we would need three separate theories to explain bonding? No one knows. That's true. No, I don't even know half the time, right? So the idea behind this is that these three theories differ with respect to one another in kind of a reciprocal relationship between accessibility versus actual explanation of what we really see, right? So Lewis theory is going to be the most accessible theory that we have. Okay? Anyone can make Lewis structures. You guys made Lewis structures already in the lab this semester before we even talked about Lewis structures, right? So you can draw Lewis structures right now, okay? Lewis theory, though, on the other hand, doesn't explain exactly what we see all the time. It's not the best theory in explaining actual results and experimental data with respect to bonding, okay? So then valence bond theory is kind of the next little step up. It is going to be less accessible, so it's going to be harder to understand, but it's going to explain bonding a little bit better. And then finally comes the granddaddy of all of the theories of bonding, molecular orbital theory. So this is going to be the hardest to understand. It's going to be the most complex. It's also going to be the most important for when you move on to organic chemistry, right? If you want to be successful in organic chemistry, understanding molecular orbital theory will be important. But because it's so complex, it also means it explains bonding really, really well, right? So it essentially takes quantum mechanics, applies it to bonding, and explains bonding in terms of quantum mechanics, which is really what's actually happening in the actual world today, okay? Okay, all right, so we're going to start with Lewis theory, which again is the most accessible, the easiest, but is going to have the most exceptions to it, or the most issues with it at actually explaining bonding, okay? So Lewis theory, big idea behind this is going to explain bonding in terms of valence electrons, okay? What we're going to get out of Lewis theory are going to be models, which is what we call Lewis structures. So we're going to draw our little bonding of molecules in terms of Lewis structures. These are also called electron dot structures. Lewis theory and Lewis structures are going to kind of be the bedrock of bonding, right? We're always going to start, regardless of what we're even trying to explain, with drawing the Lewis structure of a molecule. It's going to be kind of something that you're going to continuously use throughout the remainder of the semester as well as into organic chemistry, okay? So Lewis theory is going to help us understand and predict a couple of different things. One of the biggest one is the shape of molecules. So shape and overall three-dimensional structure of molecules is a very important tool with respect to Lewis structures, as well as molecule polarity, and we'll talk about that towards the end of the chapter. Okay, so Lewis theory and Lewis structures. So what's the big idea behind Lewis theory, okay? So Lewis theory focuses on valence electrons. So what are the valence electrons in an atom? They are going to be the electrons that are defined as those in the outermost principal energy level, right? So if I drew, let's say, the electron configuration for carbon. So does anyone know the electron configuration for carbon? So 1s2, and then we move over 2s2. And then who comes next? Which orbitals do we fill next after 2s? 2p. And there are two of them that go in there. So this is the electron configuration for carbon. Who are the valence electrons? Who are the electrons in the outermost principal energy level? All of the electrons in which number? 2, right? So outermost principal energy level is N equal to 2. So all of the electrons that are in that N shell are the valence electrons. So the 2s2 and the 2p2 are all of the valence electrons. What are the rest of the electrons? What are they called? They're not valence. What are they? They are core electrons, right? So all of the other electrons are the core electrons. And what are they characterized by? What electrons are they? Where are they at? They're in the filled lower orbitals, the filled lower shells, okay? So everything that's not valence is essentially core. It's in these filled lower energy levels. Okay, so totally for carbon, how many valence electrons does it have? 4, right? So remember the superscripts refer to how many electrons are in each orbital. So there are 4 valence electrons for carbon, and then how many core electrons for carbon are there? 2, right? So 2 core electrons. Okay, so why does Lewis theory focus on valence electrons so much? So number one, big important thing to note, valence electrons are held the loosest with respect to atoms, okay? Why would they be held the loosest? What are they farthest away from? The nucleus, right? So the nucleus is what's holding these electrons in. The valence electrons are the ones on the outermost principal energy level, so they're the ones that are going to be held the loosest by the nucleus, okay? With respect to bonding, what are we going to be doing with bonding? We're going to either be transferring in an ionic bond, or doing what if we're making a covalent bond? Sharing, right? And so if we're going to be transferring electrons, we're going to be sharing electrons with other things, we're probably going to want to do that with the electrons that we held the loosest, right? And so that's why valence electrons come into such an important role with respect to bonding, because again, they're the ones that are going to be participating in bonding, okay? So because of that, Lewis theory focuses on the behavior of valence electrons. And that's what we focus on with respect to drawing Lewis structures, is valence electrons. Okay, so valence electrons is going to be super important. How do we know how many valence electrons something has without having to draw out the electron configuration every single time? Right, so if we're dealing with main group elements, so remember main group are the first 2 columns and the last 6 columns. If we're dealing with main group elements, there were 2 different ways that we could categorize the columns in the periodic table. There was the 1A, and that was all of the main group that moved over to 3A. What were the transition metals called right in the middle? What do we categorize them as in this little scheme? We called these Bs. So we labeled the columns as the Bs for the transition metals. How many rows, or how many columns, pardon me, do transition metals have? Depends on how many electrons you can put into your 5d orbitals. 10. So there are 10, essentially, columns that we ignore when we're actually looking at main group. Okay, so the transition metals make up this little interior, ignore them entirely. Then, based off of what column it is essentially going to tell you how many valence electrons it has, as long as we're dealing with main group. So for hydrogen, lithium, sodium, this is in column 1A. How many valence electrons does column 1A have? 1. 1 valence electron. What about column 2A? How many valence electrons does column 2A have? 2. What about 3A? 3, right? So moving on all the way to 8A, which is our noble gases. How many valence electrons do our noble gases have? 8, right? So this is a very quick and easy way to determine, based on the position in the periodic table, how many valence electrons an atom has, okay? Okay, so that's great. What's next? Now we're going to start drawing our Lewis dot structure, okay? So a couple things to note about that, the way we actually categorize things here. Number one, what we represent electrons as in our little Lewis dot structures is dots, okay? So electrons, we are going to represent as little dots like this, okay? Most importantly, what type of electrons are actually going to be represented in our Lewis dot structures? Valence electrons, right? So we only represent our valence electrons as these tiny little dots, okay? All of the core electrons and all of the nucleus as well for an atom is going to be represented by the chemical symbol, okay? So the nucleus as well as the core electrons are going to be represented just by their chemical symbol. So So for example, if I wanted to draw, let's say, the Lewis dot structure for just an atom of aluminum, nucleus, core electrons is going to be represented by the chemical symbol, and then how many valence electrons would aluminum have? 3, right? So it's in column 3A. There are 3 valence electrons, and the way I represent that in my little Lewis dot structure is just as single electrons around the 4 quadrants of aluminum. Why don't you think I would put them all together? Just like something like this. What's wrong with that? In theory, there's nothing really wrong with respect to just putting them all on aluminum. That's not what we do, though. But with respect to not pairing them early, what would that kind of be violating? Right, so notice I put 1, 2, 3, and I didn't say 1, 2, 3. Why wouldn't I do that? What principle would I kind of be violating in doing that? So remember when we put electrons into orbitals, and we put them in singly first, and then we went back and paired their spin? What was that called? Hund's rule, right? So we essentially put them around the outside, and we follow Hund's rule. We put them around the outside singly first, and then we will come back and pair their spin. So for example, if I were to represent phosphorus, phosphorus has 5 valence electrons. I would represent them singly first, and then I would come back and pair their spin, okay? Okay, so this is how we're going to actually represent our valence electrons, our core electrons, and then everything else with respect to the atom in Lewis dot structures. Okay, so what's next? We're going to ignore atoms. We don't care about atoms, right? What are we trying to do here? Trying to make molecules. How do we make molecules? Make bonds, right? Bonds and molecules, exactly what we have to deal with, okay? So what is the big idea, or the big central theme behind Lewis theory, okay? So what Lewis theory posits, or what it essentially hypothesizes, is that atoms bond together because they're going to lower their potential energy. Okay, so atoms will come together, they'll be at a really high potential energy state. When they come and make a bond, that's going to lower their potential energy. If that does so, then we're actually going to see a bond formation. Okay, more stable molecules going to be lower potential energy. The idea behind Lewis theory is that it states that atoms are going to do that by obtaining a series, or 8 various electrons around them in their valence shell. Okay, so that's the big idea behind Lewis theory. They're going to lower their potential energy by obtaining 8 electrons around them. Okay, this 8 electron idea is called the octet rule. So octet just means 8. Okay, so everyone in Lewis theory is trying to obtain 8 electrons around it. So we can utilize Lewis theory to explain both ionic bonding as well as covalent bonding. So for example, if I drew the Lewis dot structure for sodium, so sodium, how many valence electrons does it have? First column of the periodic table, it has 1, right? And I drew the Lewis dot structure for chlorine, which lies in column 7A. How many valence electrons does chlorine have? 7, right? Why do we see a transfer of electrons between sodium and chlorine? In this reaction, who gives up an electron? Sodium. Who takes the electron? Right? So we're left with something that looks like this. Why would chlorine want to do that? How many electrons does it have around it right now? 8, right? That's a lower potential energy state for it, so it's going to do whatever it can to get 8 electrons around it. What about sodium? Right? Sodium, beforehand, had an electron configuration of neon 3s1. When it loses that electron in the 3s orbital, who are the new valence electrons for sodium? So we draw out the electron configuration for neon. We have 1s2, 2s2, 2p6. If these are gone, who are the new valence electrons for sodium? The 2s and the 2p. How many electrons are there? 8, right? So by doing this, they both have 8 electrons, right? That is the entire idea behind Lewis theory. We're trying to get 8 electrons. When things have 8 electrons, if they need to give it or they need to share it, then everything's going to be much more stable, and bonds are going to form as a result of that. Okay? Okay, so this is ionic bonding, which is not really what we care about too much in this chapter. Instead, we're going to be dealing with covalent bonding, right? So this was a transfer of electrons. With covalent bonding, what are we going to be doing instead? We're not going to be transferring electrons. We're going to be doing what? Sharing them, okay? So now, that's the big idea behind Lewis theory in terms of covalent bonding, is we're going to be sharing electrons so that everyone obtains an octet, 8 electrons around them, okay? Okay, so let's try to consider this when we consider covalent bonding. All right, so now let's think about something like water, right? So we know that water has a chemical formula of H2O. If we start to draw out the Lewis dot structures for our atoms that are involved, we have oxygen. How many valence electrons does oxygen have? 6, right? So 6 valence electrons for oxygen. So we'll draw those around our little oxygen, and then we'll pair, okay? And then hydrogen. We have a little hydrogen that comes along. How many valence electrons does hydrogen have? Just a little one guy, okay? So we have one hydrogen, and we have our little oxygen together. What they're going to do in forming this covalent bond is they're going to share their electrons. So we've got an unpaired electron here and an unpaired electron here. When they combine and share their electrons, the way we represent that is this nice little 2 dots in between the two, okay? All right, so hydrogen, how many electrons does it have around it right now? 2, right? So anytime we have a bond, we get to count those electrons towards both of the atoms, right? So hydrogen has 2 electrons. Is that okay for hydrogen? Yes, it is. This hydrogen is one of the exceptions to this. Hydrogen can only obtain what is called a duet, right? So it can only have 2 electrons total. So hydrogen's fine. What about oxygen, though? How many electrons does it have around it right now? So right now we have 2, 4, 6, and then 7. What else does it need to do to get an octet of electrons? If we have another little hydrogen pop on by, has another little electron, what can they do? They can share their electrons with respect to one another, and we end up with HOH. Right? Now, how many electrons does oxygen have? 8. How many electrons does hydrogen have? 2. Everything's good, right? Everything's happy. Why does water form? Because this lowers the potential energy with respect to just single oxygen and single hydrogens, right? This guy with his 8 electrons, super happy, super stable. That's why we actually see it form. Okay, so a couple of things that we have to define with respect to this structure. Go ahead and redraw it again. So I'll go back to black. We've got hydrogen, oxygen, hydrogen, and then we've got these 2 electrons around oxygen. So there are 2 different types of electrons in this structure right now. Okay, there is what we call bonding electrons or bonding pairs. So bonding pairs comes in pairs. Right now we have this guy that's a bonding pair. It's forming a bond between 2 things, and this guy. So in this structure, how many total bonding pairs do we have? 2. So for bonding pairs, we have 2 pairs. How many total electrons is that, though? 4. So note that a pair is 2, right? They're always going to come in 2s with respect to all of these bonds that we form, for the most part. So these guys are our bonding pairs. What about these guys up here that lie on oxygen? These guys aren't bonding with anyone, right? So we call these either lone pairs or non-bonding pairs. And again, for oxygen, how many lone pairs lie on oxygen right now? We have 1 up top, and we have 1 down below. So how many lone pairs lie on oxygen? 2 pairs. How many total electrons is that? 4 total electrons. How many lone pairs lie on hydrogen? None, right? So you're just looking for lone pairs, things that just lie on these single atoms themselves, okay? Another thing to note, I don't like to draw Lewis structures like this, okay? I don't like the dots. I will draw dots for lone pairs, but for me, and what you should move on to further on that you get, I like to represent bonds as single lines. Okay, so the better structure with respect to water would be a single line and a single line to represent what we call a single covalent bond. How many electrons, when I draw these, this is what happens when I try to talk and write, a single covalent bond, how many electrons are in each of these lines? That's the important thing to note. 2. So each line is always still just 2 electrons. Okay, and unfortunately, I just essentially stated on the next slide, right? So I get ahead of myself. All right, so again, better way to draw water would be with lines to represent these bonds, and one pair of electrons, one bonding pair, gives us our little single covalent bond. Okay, super easy. Now, what's next? What other types of bonds are there? There's double bonds, right? So why would we ever have a double bond come into account, right? So let's imagine that we have an oxygen, and we'll draw our little Lewis dot structure for oxygen, and it's around another oxygen. And we'll draw our little Lewis dot structure for this oxygen, right? So now, same type of thing, we have our little electrons can come together and share with each other. If we only form one bond there, then how many electrons does each oxygen have? Just 7, right? So now, what do we need to do to get everyone with 8 electrons? Super happy. Then we have another little set of electrons that are unpaired together that can form another bond, right? So we make this. We have oxygen forming a double bond with another oxygen. And again, if we wanted to draw it with all these stupid little dots, we could do that. Okay, so this guy is what is called a double covalent bond. How many electrons are in our double covalent bond? 4 total electrons, right? So essentially 2 bonding pairs. Super easy. If we look and count our electrons, we've got 8 that go to this guy, and we've got 8 that go to this guy. So everyone has their octet, everyone is happy, okay? What about if we have something like nitrogen? Poor nitrogen only has 5 valence electrons, right? Comes into interaction and encounter another nitrogen, which only has 5 valence electrons. If we want to form bonds to give it 8, we could form this bond, that would only give it 6. We could form this bond, that would give it 7. Now we could form this bond, that would give it 8 for both of them, okay? So what is this going to result in? A triple bond, right? So a nitrogen, pair with a nitrogen. How many lone pairs does each nitrogen have? Just 1 lone pair of electrons. Lone pair. How many electrons does each nitrogen share with one another? 6 total electrons. So a better way to draw this would be a nitrogen, 3 lines, 2 lone pairs on each one, 1 lone pair on each one, right? Okay, so this is called a triple covalent bond. Awesome. All right. Now, how are we actually going to go about drawing Lewis structures, right? So I walked through, I said, oh, look at this. We can like put these guys together, and we can do this, and we can do that. Do you think you're actually going to try to utilize that when I want you to draw these very complex structures? No, right? So instead, what's going to happen is you guys are going to follow these 4 steps that I provide for you in the next few slides on how to actually go about drawing the correct Lewis structure every time, okay? So what is the first step in drawing the Lewis structure for a molecule, okay? We're going to take our compound. So for this guy, we want to draw the Lewis structure of NF3, okay? Number 1 first step is to draw the correct skeletal structure. So what I mean by that is the correct atom that's in the center surrounded by the correct things on the outside, okay? That may not be as simple as it seems. So there's going to be 2 different positions in each structure that I'm going to define, okay? And I'm going to go ahead and draw the correct structure here for this nitrogen trifluoride. Nitrogen is going to go in the middle. We're going to call this our central atom. The 3 fluorines are going to go on the outside of the nitrogens, or 1 nitrogen, okay? These guys, these fluorines on the outside, we call these our terminal atoms. They're in the terminal position. They are not bonded to anything else except for our central atom. Now, big question would be, I told you that this is the correct skeletal structure for this. How would you know? How would you know what goes into the center and what goes into the outside? So there's a term that we're going to introduce later on. It's called electronegativity. When you do come into that term, and you know what it means, and you can know that the least electronegative element is always going to be in the center, okay? Another good, helpful little hint is whatever comes first in the chemical structure. Who comes first in this chemical structure? Nitrogen. Usually that's the least electronegative element. So whatever comes first is usually going to be in our center spot, and then everything else is going to be terminal to it. Okay? Okay, so step number 1, correct skeletal structure. All right, so step number 2, we are going to sum all of the valence electrons for our structure. Okay, so if I go ahead and redraw my nitrogen and my fluorines, next step, we need to know how many valence electrons all of these atoms are bringing to our structure. Okay, so what are we going to do for that? Number 1, we've got nitrogen. How am I going to know how many valence electrons it has? I'm going to go to something. It's called the periodic table. Right? I'm going to look at what column it's in. What column do you think nitrogen is in? Column with respect to main group, 5th column. So nitrogen is going to bring us 5 valence electrons. 5 electrons. And then fluorine. What column is fluorine in? 7. I don't know how to do 7 with my hands. 7. So how many valence electrons is fluorine going to bring us? 7. How many of them are there? 3. Right? So we have 3 times fluorine gives us 3 times 7. What is 3 times 7? 21. So total, when I sum all of these guys together, we have 26 valence electrons to distribute. Okay? Step number 2, sum the valence electrons. Step number 3, sum the valence electrons. Okay, cool. We're going to start to distribute. Okay, so we have 26 to get rid of. We have our skeletal structure. So this is kind of where the hard part comes in, and people always get really confused or they do it incorrectly. Okay, first thing you're going to do is you're going to make single bonds between the central atom and each of the terminal atoms. Okay, so number 1, I'm going to come in and draw a line between my central atom and all of my terminal atoms. Okay, how many electrons have I put into the structure at this point in time? 6. What's next? I'm going to fill the outer octets. Right, so everything, all of my terminal atoms, I'm going to go ahead and I'm going to go through and fill their octets. How many do I need to put into each fluorine to fill its 8 electrons? 6, right? So I'm going to go ahead and put them in as lone pairs on each of my terminal atoms. Then what am I going to do? I'm going to figure out, now that I put in everything that I have, how many electrons have I actually put in? I put in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. How many do I have to get rid of? 26. So I have 2 more electrons. What do I do with those 2 electrons? I'm going to put them as a lone pair on the central atom, right? So you've distributed everything. You've filled in all of the outer octets. If you have excess electrons, you're then going to put them as a lone pair on the central atom. Okay? That's 26. Is everyone happy in this structure? Everyone has an octet of electrons. Okay, so this is good. Nitrogen has 8, fluorine has 8, everyone's super happy. All right, so then there may be the question, well, how do I know when I'm going to make double bonds? All right, so for example, I'm going to use CO2 as a good way to illustrate when you would actually come into a situation when you need to make multiple bonds. So we're going to do the same exact thing for CO2. Okay, so CO2, carbon, how many valence electrons does carbon have? 4. How many valence electrons does oxygen have? 6, and there are 2 of them, so that's going to give us 12 electrons total. That gives me 16 electrons to distribute, okay? When I draw my skeletal structure for this, who goes in the middle? Carbon, right? Usually, again, the least electronegative element will come first in the chemical structure. So carbon's going to go in the middle, and I'm going to surround it with the 2 oxygens, because those guys are terminal. What do I do now? So I've summed up my valence electrons. I've drawn the skeletal structure. What's next? Single bonds, right? So I'm going to make single bonds, connecting terminal to central. And then what am I going to do? I'm going to fill the outer octets, right? So I go in, I do that, I do that, I do that. Oxygen, they're good. They have 8 electrons. How many electrons have I gotten rid of at this point in time? 16. How many did I have to get rid of? 16, right? What's the problem with this structure right now? Carbon doesn't have an octet, right? So when do you need to make double bonds? When do you need to make triple bonds? When you have filled in the outer octets, and your central atom, you've gotten rid of all of your electrons, and your central atom does not have an octet, okay? At that point in time, you'll take your little eraser, and what will you do? You're going to go in, you're going to take one of these lone pairs that's on the terminal atom, and you're going to make a double bond with it. So for this little oxygen that's over here that I've just taken the lone pair of electrons from, how many electrons does it still have around it? 8, right? How many does carbon now have? Just 6. So what am I going to do? I'm going to do the same thing on this side. Take a lone pair, make a double bond. All right? That's when you make double bonds. That's when you make triple bonds. Yes?
It doesn't matter which lone pair you take, right?
So we'll talk about that in a second. That's a good point. I could have gone ahead and taken, let's reverse this guy. I could have gone ahead and taken this one and make it a double bond, okay? In theory, right now, with what I've introduced you, there is nothing wrong with that structure, right? But just trust me on this one. We'll come into the reason why this is not the correct structure for CO2 in a few slides. Darn it, give me my big, I want my big eraser. Okay. Okay, double bond. Yes?
Did you guys go back to step 2 really fast?
Step 2, okay. So step 2 is the actual number step 2?
Yes.
Yes. Okay, so that's when you make double bonds, okay? When you have distributed everything, you've given the terminal atoms octets, but that central atom does not have an octet. So one more little thing I want to go over, and then I will let you guys make as many Lewis structures as you want. What if we have an ion? What if we have something like a polyatomic ion, something like carbonate? How is that going to affect how we actually go about drawing this Lewis structure? Yes?
You have to take into account the number of overall valence electrons for the elements themselves plus its charge.
Okay, good. Yes. So the only way that this is going to differ is when we sum our valence electrons, we're going to take into account the atoms themselves. So carbon has 4 electrons. Each oxygen for carbonate has 6. So 3 times 6. Bad 6. What is that? 18. What is 4 plus 18? 22. And then now, to take into account the overall charge of the molecule, what am I going to do? Am I going to add electrons, or am I going to subtract electrons from my total electron total? I'm going to add them, and I'm going to add the actual charge. So how many electrons should I add for carbonate? 2 more, right? So when I sum my valence electrons, that's when the charge comes in. So this is going to give me 24 overall valence electrons. Okay, so we'll leave this at this one. Just note, if it is a charge, you need to add in or subtract in, and then I will actually go through the drawing of this one in a second. Okay, so go ahead. Let's try some. I want you guys to draw the Lewis structures for carbon tetrachloride, H2S, and then nitrite. I want you to ignore this one. It's bad. Don't want to go there yet. So you're going to draw these Lewis structures. In Socrative, there's no way for you to draw the Lewis structure in Socrative, but what I do ask is how many lone pairs are on the central atom when you actually draw the correct structure. So draw them, and then the question I ask is a little bit different. Okay, so go ahead and get your answers in if you haven't. We'll go ahead and start going over these. So for carbon tetrachloride, how many total valence electrons were there? So carbon has 4. How many does each chlorine have? 7. So what is the total number of valence electrons that we have to get rid of? 32. All right, so when we do that, who goes in the middle whenever I draw the skeletal structure? Carbon. Carbon is least electronegative. Chlorine, chlorine, chlorine. Make single bonds, fill in the outer octets. When I do that, how many do I get rid of for electrons? 32, right? So there's no more electrons to put on carbon, so then how many lone pairs does carbon have? 0, okay? Okay, so we're skipping SO2. What about H2S? How many valence electrons does this molecule have? So we get 2 times 1 for the hydrogens, plus how many does sulfur have? 6, so we get 8 total. So who goes in the middle? This is kind of a tricky one. I probably should have mentioned it earlier. Sulfur does, even though it comes last. One thing to note, hydrogen can never be a central atom. It always has to be terminal. So regardless of if it's written first, hydrogen is always terminal. So we go ahead, connect our little central to our little hydrogens, which are terminal. That's 4 electrons. And then we have 2 more to get rid of, or 4 more to get rid of. They go as lone pairs on the central atom. Total 8 electrons. How many lone pairs does sulfur have? 2 lone pairs of electrons, okay? So then last, we have NO2 minus. So NO2 minus, who is going to be my central atom? Nitrogen, surrounded by these oxygens. How many total electrons do I have? I have 5 plus 2 times 6. And then what else do I need to add in? Another 1 for the negative charge here. So this is going to be plus a 1. What is that? 18? Yes. Okay, so I go ahead and I make my little single bonds, and then I fill in my little outer octets. Everything's going great. How many electrons have I gotten rid of at this point? 16. So then what do? I have left over 2 more electrons. Where do I put them? I've been in Oklahoma too much. I put them as a lone pair on the central atom, right? Is this the correct skeletal structure? Am I done quite yet with this one? So I've gotten rid of all of my electrons, so that's great. What's the problem with nitrogen right now, though? It doesn't have an octet, right? So for the correct skeletal structure, the correct Lewis structure, which is what we're talking about, what do I need to do to give nitrogen an octet? I'm going to take this guy away, and I'm going to make a double bond. So this would be the correct Lewis structure for NO2. Also note that when we are dealing with these polyatomic ions, to denote the charge on the ion, we'll use brackets, and we'll put the charge on the outside. So NO2 minus has a 1 minus charge. We denote that in the Lewis structure with the brackets and the charge on the outside. Okay, so a couple more things before we finish for today. So I told you at the very beginning that Lewis theory was great because it's super accessible, right? It's super easy to draw these Lewis structures. The problem with it was, though, is that it wasn't actually that good at explaining things. Okay, so there are a couple of exceptions that we're going to have to consider when dealing with drawing Lewis structures. The first one is the fact that, while we've said everything wants an octet of electrons, some things actually are okay with less than an octet of electrons. And so those some things, or those some atoms, specifically, are beryllium and boron. Okay, so if you have a compound where beryllium is the central atom, beryllium is actually happy with only 2 bonds to it and 4 total electrons around it. It does not need to have an octet. This is one of these exceptions that you just have to kind of remember. Same thing with respect to beryllium. Nope, boron. Did I say beryllium originally? Beryllium likes 2 bonds. Boron only needs to have 3 bonds. So if it's okay with only 3 bonds around it, how many electrons is it okay with? 6, right? So boron is okay with 6 electrons. Everything else, though, in period 2 has to have 8. Beware number 2, exception to the octet rule number 2. Sometimes, especially when we deal with nitrogen-containing compounds, we will end up with an odd number of electrons. Okay, so that is okay. It's all right. Again, these tend to be compounds that contain nitrogen, and nitrogen tends to have only 7 electrons around it when we actually draw the correct Lewis structure. Okay, so sometimes this will occur. These are what are called radicals, so it doesn't have a paired electron. They're unstable, and they tend to decompose, but they will be present every once in a while. Okay, and then exception number 3, which is really important to know. Okay, so sometimes you'll be dealing with Lewis structures where the central atom can actually obtain more than 8 electrons. Okay, so this is going to be anything in period 3 and below. Okay, so we think about this, it kind of makes sense. When we're dealing with everything in period 2, which is n equal to 2, what are the orbitals that we're allowed to access in period 2? Period 2 has, for valence electrons, has the 2s. And how many electrons can go into the 2s orbital? 2. And then what else does it have? We have the 3 2p's, right? So 3 2p orbitals, 2 electrons in each one. How many total electrons can the p's hold? 6. So in n equal to 2, 6 electrons, or 8 electrons, that's all we can have, right? What happens when we go into period 3, where our principal quantum number is equal to 3? For valence in this shell, well, we won't even deal with valence, but what is, with respect to orbitals, what do we introduce when we get to n equal to 3? We introduce the d orbitals, right? And so because of that, the d orbitals give us the ability to make more bonds or have more electrons than just 8, so that anything in period 3 and below can have more than 8 electrons around it. This could be 10 electrons, it could be 12 electrons, etc. Okay? Okay, so how would we actually go about dealing with something like this? So we can draw the Lewis structure for sulfur tetrafluoride to kind of illustrate this. So in drawing this Lewis structure, what is my first step in doing this? First step is what? My little rules, 4 easy steps to drawing Lewis structures. Skeletal structure, that's usually where it starts. But you can also count the valence electrons first if you want to too. So skeletal structure, who's going to be my central atom here? Sulfur. Sulfur is going to be surrounded by our 4 fluorines, which are terminal. And then we're going to count our valence electrons. So how many valence electrons does sulfur have? 6. So let me move this guy over. 6 electrons. And then how many valence electrons does fluorine have? 7. There are 4 of them. So overall that's 28. 6 plus 28, is that right? Yes, is 34. 34 electrons to get rid of into this structure. So then do my same exact thing. I make my little single bonds, and then what do? Fill in the outer octets. So I go 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've gotten rid of 32 electrons. How many did I have to get rid of originally? 34. So now what do? I'm going to add a lone pair to sulfur. So I'm going to pick a little quarter. I'm going to add the lone pair together. They don't get separated. That's okay though. How many electrons does sulfur have around it at this point? 10. It's fine. Where's sulfur at? Period 3. All right. You look across. Look at the row it's in. It's in row 3. That's okay because sulfur has d orbitals, so we can make more bonds. It doesn't just get stuck with 8 electrons. Okay, so we'll go ahead and try that. We've got 2 structures. And I want you guys to tell me, when you draw the correct Lewis structures for these two, how many lone pairs of electrons do you have on the central atom? Okay, so we'll go ahead and go over these. Most of you guys got these correct. We're at about a 71% and a 77% correct rate. Okay, so with respect to these, xenon dichloride. So our xenon is going to be our central atom. What's great to note about xenon with respect to where it's at on the periodic table? It is in period 3 and below, right? So that means what? It can have an expanded octet, so more than 8 electrons. So when we go ahead and sum up the valence electrons for these guys, how many does xenon give us? Xenon is a noble gas. It gives us 8. And then both of the chlorines give us 7. That's 14. 14 plus 8 is 22. So make single bond, dot, 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 dot. That gets rid of 16. What do I do with the rest of the 6 that I have left? just a lone pair on xenon. And so just by convention, we try to pick a corner and put the pairs together. So then how many lone pairs does xenon have right now? 3 total lone pairs. 3 lone pairs. Okay, so then IF5, we've got iodine, which gives us 7, and then fluorine, which gives us 35. So 35 plus 7 is 42. Lots of electrons. So iodine comes in the center. We get fluorine, 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 fluorine. Single bonds, single bond, single bond. Fill in the outer octets. How many electrons do I get rid of when I fill in the outer octets? 40. So 40 gets rid of those guys. Everything on the outside is happy. What do I do with that last 2 electrons? They're just going to go as a lone pair on my iodine. So that means for iodine in this structure, how many total electrons does it have around it? 12, which is okay. It's fine. It's because it's in period 3 and below. It can expand its octet. Okay, so I'm going to go ahead and stop there. I want to make a note about something though, right? So with respect to Lewis structures, this kind of forms the basis behind what we do next, chapter 2. So if you cannot correctly draw Lewis structures, you're not going to be able to correctly identify the molecular geometry. You can always Google it, right? But you can't Google it on an exam. Or you can try to Google it on an exam, and then hopefully I could catch you. Okay, so just note that, right? You need to be able to do this on your own. Okay, so with respect to exam, I'm going to record that. So a couple of things to note. We do have an exam on Thursday, so please bring your Scantron on Thursday. There is an exam review. Do you guys get those emails? Have you been notified of that? Okay. Yeah, so it's today at 3 in the tutoring center. So you should go to that if you have time. I think that's it. So yeah, all the homework for 6 and 7, that was due on Sunday. So that is closed. There is a homework for chapter 8, which deals with Lewis structures. That is open, it's available. So maybe try to use that to help practice for this material before the exam on Thursday. Okay, so today I'm going to finish off chapter 8. We have like a few just brief little slides to do. I'm going to start on chapter 9, but I have like a little point that I'm going to get to in 9, that once I get there, we're going to end today, regardless of where we're at, because you guys should maybe go study for the exam, okay? Okay, so with respect to where we left off, so the last thing that we were talking about on Thursday was bond energies, right? This was defined as the energy required to break a bond, okay? And we had utilized these bond energies to estimate the enthalpy of a reaction, right? So I'd given you guys a little equation, which was the sum of the bonds formed minus the sum of the bonds broken, etc. Whatever it is, you guys know how to do that at this point in time, okay? So today we're going to kind of pick up back where we left off with respect to that trend, but instead of talking about bond energies, we're going to talk about bond lengths, okay? So the overall length of a bond. All right, so when we think about bond lengths, what we're looking at, or what we're trying to essentially measure, is what we call the distance between the two nucleuses, okay? So when we're thinking about bond lengths, what we're looking at is the distance between two nuclei that make up a bond, okay? So that's how you can understand bond lengths. So what are the trends with respect to bond lengths? So it's very similar to what we saw with respect to bond energies, okay? So they're going to be two general trends depending on what we're looking at, okay? So number one, the first trends deal with how many electrons a bond contains, right? So for example, if we look at the difference between a triple bond versus a double bond versus a single bond, how do these guys differ with respect to the number of electrons? How many electrons does a triple bond have? 6 electrons. So a triple bond contains 6 electrons. A double bond, how many does it have? 4 electrons. And then a single bond has 2 electrons. So the more electrons that a bond contains, the shorter the overall bond. Okay, that is the big trend with respect to number of electrons. So the more the electrons that make up a bond, the shorter the bond. Okay, so then a triple bond is going to be much shorter than a double bond, much shorter than a single bond. So then the second little trend deals with bond lengths as we move across a period. So this is very similar to what we saw with bond energies, okay? So what we're looking at in the second little trend is the bond length as a function of the size of the atoms that are actually binding together, making a bond, okay? So with respect to size of atoms, we utilize our trend in atomic radius to kind of gauge the overall size of an atom. So what happens as we move from left to right across a period, across a row, with respect to the atomic radius of the atom? Do they increase or decrease? So as we move from left to right across a period, we see a decrease in atomic radius. So again, this is just a measure of the overall size of atoms. What about as we go from top to bottom? As we go from top to bottom with respect to the periodic table, what happens to atomic radius? We see an increase. Okay, so we're going to see very similar trends with respect to bond lengths. So the shorter the thing that is making up a bond, the smaller the bond length, okay? So if we compared bond lengths between atoms moving across a period, so we compared, for example, the bond length of carbon to carbon, or carbon to nitrogen, or carbon to oxygen, between carbon and nitrogen and oxygen, who is the shortest, who is the smallest atomic radius? Because these guys all exist in the exact same row, the exact period. So same row between carbon and nitrogen and oxygen. So who is the smallest atomic radius? Oxygen, right? So oxygen has the smallest radius. So because of that, we're going to see the shortest bond between carbon and oxygen. Okay, so as we move from left to right, across a row, across a period, we're going to see a decrease in bond length. And again, this just goes back to the overall size that you guys should know because you understand the trends in atomic radiuses. Okay, so as we move from left to right, we're going to see a decrease in bond length. So things at the right side of the periodic table are going to have smaller bond lengths. What about as we move from top to bottom? We see an increase in atomic radius. So how is that going to translate in terms of bond lengths? They're going to get larger, right? So as moving from top to bottom, we're going to see an increase in bond lengths. And this is very similar to what we saw with respect to bond strengths, right? Because overall, the longer the bond, the weaker the bond. Okay, so the longer the bond, the less energy is going to be required to break it. So the smaller the bond energies. Okay, so these all kind of go hand in hand with respect to one another. Okay, so the more electrons, the smaller the bond, the smaller the atomic radius, the smaller the bond, etc. Okay? Okay, so this last little bit that we're going to talk about, everything that we've been looking at thus far has been dealing with covalent bonding, right? So covalent bonding involves the sharing of electrons. So we haven't talked necessarily about ionic bonding. And so that's what we're going to kind of mention very briefly at the end here. Okay, so we're going to talk about ionic bonding and how we can kind of estimate overall ionic bonding strength, kind of like we just did with respect to covalent bonds. Okay, so as a reminder, how do I know that I have an ionic bond? What type of compounds am I dealing with in ionic bonding? Metals and nonmetals, right? And so we can actually calculate that using differences in electronegativities now. If I had an ionic bond, what would my difference in electronegativity be? So this is going to be a difference in electronegativity greater than 2.0 using our electronegativity scale in our textbook or in this slideshow. Okay, so a couple things about ionic bonding, okay? With respect to ionic bonding, a lot of things actually go into forming the ionic compound. Okay, so for example, if we're going to form something like sodium chloride, we know that sodium has a +1 charge and chlorine has a -1 charge. Okay, so to form this compound, sodium first off has to lose an electron. Okay, we have talked about trends with respect to things losing electrons. In Chapter 7, what was this called? This process of losing an electron or having an electron plucked away from you? We, I guess, denoted it via an energy that we measured. We could kind of understand the energies of this process. So what is this called? Ionization energies, right? So removing an electron from something, this is usually referred to as the energy, the ionization energy. All right, so that has its own specific energy that we're not even going to consider at this point in time. What about chlorine taking an electron? That had something else. We called it something else. There was a different trend. The affinity, if you will, for just grabbing an electron from something else. What was this called? Electron affinity, right? So those are two different energies that already go into this process that we're not even going to consider when we consider this ionic bond strength, if you will, right? So just as a reminder, ionization energies, were these positive or negative? Did it require energy or did it release energy when we plucked away an electron from something? They're always positive, right? It always requires energy to remove an electron from something. What about electron affinities in general? Do you release energy or do you absorb energy when you gain an electron? Absorb it, well, yeah. Absorb it, no. You release it, right? So this is going to be negative. So in general, ionization energies are always positive. It's an endothermic process. Electron affinities are usually negative. This tends to be an exothermic process, though it depends on the actual thing that we're looking at. Okay, so the process of losing an electron, the process of gaining an electron, that is what initially gives us our two charged ions that are going to form this ionic compound. Okay, so now how do we kind of model this idea of ionic bond strength? So we utilize something called the lattice energy. Okay, so this goes into this entire process, which is called the Born-Haber cycle. I'm not going to talk about that today at all. If ever, you'll never hear about this from me. But for the most part, with respect to lattice energy, we model this as the energy that is released when ions come together and form their ionic compound. Okay, so overall, the real meaning of lattice energy is the energy that is released when a sodium combines with a chloride to form its solid sodium chloride. Oops. This process, in general, overall, this lattice energy is going to be very exothermic. It's going to have a very large and negative enthalpy, if you will. Okay. So again, lattice energy is the energy that is released when these ions come together to form their ionic compound. We actually utilize this in the reverse, though. Okay. So if we want to estimate how strong an ionic bond is, we're going to use the reverse of this, which is going to be taking the ionic compound and breaking it apart into its component ions. And so this differs depending on the textbook that you utilize, but just note lattice energy is negative, right? And again, it's the energy released when these guys come together to form their compound. If we're going to use the reverse of this, though, what am I going to do with respect to the sign? So if I reverse this reaction up here, what do I need to do to the energy if I want to reverse the process? Just change the sign. Okay, so for the most part, with respect to these lattice energies, we write them as positive, and again, this is supposed to be denoting the energy that is required to be put in to break an ionic compound into its component ions. And so for the most part, you'll see these written as positives, and again, it's representing that reaction, but you can also see them written as negatives, which is just representing the reverse reaction, okay, them coming together. Okay, so a couple things. If we notice, we go to the textbook, there is a large list of these various lattice energies for various ionic compounds, and they differ greatly depending on the compound that we're looking at, okay? So the idea behind this is not necessarily to utilize these in any particular manner, but again, it's to get an idea of the trends in lattice energy so that we could understand, given a certain compound, who's going to have the larger lattice energy, okay? So that's what we're going to do now. We're going to focus on understanding the trends with respect to lattice energy. Okay, so to do that, we're going to come back to Coulomb's law. Okay, so Coulomb's law deals with electrostatic interaction or electrostatic energy, and it is given by this constant. So K is a constant that we don't care about, times charge 1 times charge 2 all over R, where R is the distance between the two ions. Distance between ions. Okay, so if we considered different ions, let's say that we're considering various different ions that have a +1 and a -1 charge, things like lithium chloride, sodium chloride, etc. If these guys all have the same Q, so if this is Q1 and this is Q2, and they're all the same for all of these guys as we move down, what is the difference going to be between these? And how could we kind of utilize that to predict who's going to have the largest lattice energy? So as we go from lithium to cesium, what am I doing with respect to the periodic table? I'm going from the top to cesium is at the bottom, right? Same thing, well, chlorine's the same thing. So they're paired with the same negative charge on the other side. So as I go from top to bottom, lithium to cesium, what's going to differ between these guys with respect to my little equation over here? Q1, Q2 is going to stay the same. What differs? The distance, right? The distance between them, and how is that going to vary with respect to one another? How do I change going from lithium to cesium? What happens to the atomic radius? It increases, right? So as we go from top to bottom, we see an increase in the radius of these guys. What's that going to do to my distance between my two ions? It's going to get bigger, right? So down here, cesium, because the distance between these guys gets bigger, what's that going to do to my overall lattice energy? It's going to get smaller. Okay, so at the top, lithium chloride, this is going to have the largest lattice energy because, again, the atomic radius is the smallest, right? They're going to have the smallest distance between them. At the bottom, we're going to have the smallest lattice energy because cesium is the biggest atom in this little host of atoms, and that's going to give us a smaller value for lattice energy. Okay, so that's one thing to consider. Distance between them, which comes back to just atomic radius. The second thing is you need to consider with respect to these trends in lattice energy is the overall magnitude of the charge, right? So in that first little slide, we had a +1 and we had a -1, right? But again, the overall magnitude of these charges are included in Coulomb's law, right? So this comes in the form of Q1 and Q2 over R. So as I increase the magnitude of my charges, what is that going to do to my lattice energy? Q1 gets bigger and Q2 gets bigger, what's that going to do to E lattice? It's also going to make it larger, right? So how would we increase the overall magnitude of these charges? What if we were dealing with something like calcium, which is a +2 charge, and oxygen, which is a -2 charge, okay? So sodium versus fluorine, the charges are +1, -1. Calcium and oxygen, we have a +2, -2, right? The distance between these guys ends up actually being fairly similar, right? So we have a 231 picometers and a 239 picometers. Who's going to have the largest lattice energy between sodium fluoride and calcium oxide? Calcium oxide, right? Because these charges are going to be a +2 and a -2 over the same R, whereas this guy's going to be a -1, a +1 over the same R. Okay, so the larger the magnitude of the charges, the larger the lattice energy, right? So more energy required to actually break the ionic compound. So of those two factors, we just looked at two of them, magnitude of charges and distance between, the magnitude of charges is actually going to be more important, right? So when you're comparing a different list of these various ionic compounds and you're trying to order them in order of, let's say, increasing or decreasing lattice energy, you should utilize the charge first, and then you should go to the radius of the atoms to figure out who's going to have the largest or the smallest lattice energy. Okay, so let's go ahead. We'll try that. So I have a question. I have 4 different compounds, and I want you to arrange them in order of increasing lattice energy. So when we say increasing, we're going to go from the smallest lattice energy to the largest. Okay, so let's go ahead and go over these. Most of you have gotten an answer in ish. Most of you have done pretty well, so about 68% correct rating. So when we're looking at these, the first thing I would look at is the magnitude of the charges, right? We have 4 compounds here, but 2 of them have a +1 and a -1, and 2 of them have a +2 and a -2, right? So that would be my first division. So who's going to have the largest lattice energy, the things with the +2 and -2, or the +1 -1? +2 -2, right? So we're going to have calcium and oxygen. These both have a +2 -2, and then strontium oxygen, +2 -2. I'm going to kind of divide them over here with respect to the largest stuff. So this is going to be strontium oxide versus calcium oxide. And then with respect to the smallest, because again, due to the charges, we have a +1 -1, +1 -1. I'm going to consider the difference between KCl versus KBr. Okay, so that's my first division, dealing with the magnitude of the charges. So now if I wanted to figure out who's got the smallest lattice energy between potassium chloride and potassium bromide, what should I consider as a difference between these two? The overall size, right? So both of them have potassium, so we can't consider that. But then the anion in one is chlorine and the other is bromine, right? So who's larger, bromine or chlorine? How would you know? You go to the periodic table, chlorine is right above bromine. So who's larger? Bromine, right? So bromine has the larger atomic radius, right? So it's larger overall. That's going to make the distance between them larger. So that's going to make the potassium bromide the smallest. So it's going to be less with respect to potassium chloride due to the difference between the radiuses of the two. So then if we move over to strontium oxide, calcium oxide, again, these are both +2 -2. How do they differ with respect to one another? Size again, right? So who is smaller? We've got calcium. Where does it lie with respect to strontium? Right above it, right? So calcium versus strontium. Calcium is smaller here, and strontium is larger. So because of that, strontium oxide is going to have a smaller lattice energy, right? Strontium oxide is going to be less than calcium oxide because the smaller the radius, the smaller the distance between the two, the stronger the lattice energy. Okay, so ideally, this would have been potassium bromide, potassium chloride, strontium oxide, calcium oxide. Did I get that correct? Because I get confused sometimes. That's what it's right? Yeah, okay, cool, awesome. Sometimes I talk myself out of stuff. Quite frequently, actually. Okay, so, especially when I'm tired, which is, at this point in time this semester, is every day. Okay, so, we are done with Chapter 8. That is it. Goodbye. No more.